Now, I have some demonstrations that we'll do later on for which I'll need to get close to everybody. So it would be very convenient if you could come down close to the front and the centre. And I've inspected all of these front 2 rows of chairs. There's not a redback to be found on any one of them. It's quite safe to come down and sit near the front, if you wouldn't mind. So you've had time to look at that overhead. Oh, it's drifted back. So I intend to talk about, just superficially, where harmony and consonance come from, and then the worry and the wonder of the circle of fourths. I'll explain what that circle is in a moment, but it's been the basis of a huge arithmetic industry to resolve it arithmetically. But I think that I might be the first composer to ask how you could resolve it musically. So here is a circle of fourths: E, A, D, D, G, G, C, C, F, B flat, E flat, A flat, all the way up till you get to 5 octaves. It's a rather odd chord given the notes that are in it, and let's hear it spread out over the orchestra. So there it is, the bad guy walks into the room chord. And I'm going to talk about a little composition in which I said, all right, if you've got that chord, how do you resolve it in the musical sense? How do you get from there to somewhere acceptable? You know, I mean, you can't just sort of go from there to a major chord, for instance. So how do you resolve it? How do you get out of it into something musically interesting? So that's going to be the overview, a little bit more detail. The science will start going back to at least Pythagoras and also ancient Chinese researchers who looked into harmony. The phenomenon of consonants, putting notes together in harmony, a little bit about tuning, interference of 2 different tones, an interesting thing that I'm going to demonstrate called the Tartini tones, and then this circle of fourths. And then what I'm going to do is talk about this piece of music, again, this piece of music that's got the strange chord. And I'll talk about how I went about writing that piece and what goes into composition of that. Okay, so I want to experiment a little with notes. Is anyone going to, I want someone to sing one note for me. Is there any singers around here? Anyone who can?
Yeah, there's one there who's trying to hide.
Okay. Okay, so just one note. La. Can I ask you to sing that note?
Oh, no.
All right, I'll forget about the experiment with notes. Don't worry about it. It's not terribly important, and I'll come back to it later on. It's the first time I've ever asked for that in a class or in a talk and had not a single taker. All right, so straight then on to Pythagoras. The trouble is I can't sing 2 notes at once, and that's why I did want assistance. The ancient Greek word harmonia meant fitting together, and it meant fitting together in the geometrical sense as well as the metaphorical. So a carpenter would talk about the harmonia of the joints in a piece of furniture, for instance. And Pythagoras in the Western tradition was the first to do the study of what happens when you play notes on 2 similar homogeneous strings, or even on the same string, and what is it that governs whether those notes fit together. And in particular, to quantify it, what lengths of strings, if I change the length of this string, what about it can I quantify and relate that to the harmonious nature or otherwise of a particular interval. Pythagoras is probably not the first, and probably the early experiments were done in China, but I'm not going to talk about them largely because I don't know so much about them, and they also didn't have the same influence on science that Pythagoras did. So, one of the things that Pythagoras quickly found out is that if you consider an octave, what do I mean by an octave? 1, 2, 3, 4, 5, 6, 7, 8, 1, 8 is an octave. You see, I'm not volunteering to be a great singer either. And he discovered that if you shortened the string by a factor of 2, you could get roughly an octave. So he thought exactly, measure it carefully, it's not quite, but a string length ratio of 2 to 1, doubling the length of the string takes it down an octave, halving the length of the string takes it up an octave. And if you then said, what about the fifth? So I said, 1, 2, 3, 4, 5, 1, 5, 1, 5, measure those and discover that the ratio, the length ratio was about 3 to 2. And if you said the fourth, 1, 2, 3, 4, 1, 4, the ratio was 4 to 3, and there's a few more in that series. We could say that the major third, 1, 2, 3, 1, 3, 5 to 4, 1, 6, 1, 6, 1, 6, the major sixth, about 5 to 3, etc. You could say that this study was one of the very earliest quantitative studies in experimental science, and it's had a huge influence on thought, on the idea that you could explain things mathematically, that you could be quantitative about perceptions and measurements. It really influenced the development of physics and other sciences for millennia afterwards. So it's an interesting thing to be following. And of course, if you were to ask Pythagoras or his school about this, why should halving the length of the string give a particularly harmonious interval? He and his team would probably have said, well, it's obvious. The numbers are pure and mystical and magical, and if you have two perfect numbers like 2 and 1, then anything that's related to them must sound nicely. And that might sound a bit weird to us, but even as late as Kepler, we had Western scientists saying, oh, the orbits of the planets must be in nice ratios because the divine architect would have looked for pure, simple numbers, taking the pure numbers, the mystical numbers. Anyway, it had this huge influence. We wouldn't accept that. We'd probably say, no, there must be some more fundamental reason for that. And at least for the octave, which is pretty much universal, there is. You could say that our ideas of harmony depend on physics, which I'm going to talk about, also somewhat on physiology, but also another PH word, on fashion. And it varies a little bit with time and where you happen to live. And my ideas of harmony and those of someone living in Bali might be quite different. Okay, I'm just going to quote a more modern result and to say that the frequency of a wave is equal to the speed of the wave divided by the wavelength. I might have time to talk about that if you want after we finish here, but this is not going to be a complete physics lesson. However, Richard mentioned PhysClips, our big intro physics online resource, and some of the relevant chapters would be travelling waves, standing waves, and consonants. But the importance of that is that if you take that result, you could say that a string length ratio of 1 to 2 implies a frequency ratio of 2 to 1. So that, for instance, if I have 100 vibrations a second, 200 vibrations a second, that would be a string length ratio of 2 to 1 or a frequency ratio of 1 to 2. The interesting thing is that it's not arithmetic. If 100, 200, 300, and we'd say, that second interval was smaller. It's the ratio that's important and not the difference. So there's some examples. 100 vibrations a second to 200 would give me an octave. 200 to 300 gives me a perfect fifth. So These are called harmonic ratios, ratios of small numbers. What happens when you add sounds that have their frequencies in those harmonic ratios? Well, let me draw that in a graph. So here is time without measuring it, just a general time axis. And let's suppose that I have a vibration that goes through one complete cycle in the time t, and if it were 100 vibrations a second, then each vibration would take 1/100th of a second, so the period, the time for one vibration, is the reciprocal of the frequency. So there is my 100 vibrations a second, and here is 200 vibrations a second going through 2 cycles in the time of one of the first, and here 300 vibrations a second. There it is, 3 times the frequency. And then I ask, what happens if I add 2 of those together? So if I add a note and its octave, well, you can see that because after one complete vibration of the first, the second one will have vibrated exactly twice, and so it will be ready to start another vibration that's exactly the same. So whatever this first pattern happens to be, it repeats itself. That's actually an interesting mathematical result, that when you add together harmonic vibrations, you get vibration patterns that repeat in time. You get what we call periodic waves. Each complicated vibration repeats itself exactly. The reverse of that is also true. A periodic wave can always be written as the sum of harmonics, and those 2 results are the foundation of harmonic analysis and Fourier transforms. But that doesn't concern us here. Am I getting the level about right? How many people say, oh, I'm already lost, I want to go home? Is there anyone who has some questions to ask? Level? Yes?
When you suck in helium and you talk,
Mm.
and the wave, is it more, the frequency goes up?
No. Well, the interesting thing about it, I have a webpage on helium voice. You can Google it if you like. But the interesting thing is that the voice sounds different, but the pitch actually is unchanged. It's a different timbre to the voice, but when you inhale helium, provided that you don't, you have to be cautious with it, by the way. You can cause yourself serious damage by inhaling too much, but it doesn't change the pitch of your voice. It's a very interesting question. I could come back to it, but we'll have to do that after it's outside the step here. Yeah? So, interesting question, and a paradoxical one as well, because when most people, when they hear it, say, oh, until you actually ask someone to sing with helium in the throat, you don't notice that the pitch is unchanged. Okay, so going to our Pythagorean consonances, the string lengths with those whole number ratios, the notes with those frequency ratios, we can sort of see that now there's a sort of explanation for that. We could say now we're asking, why do periodic waves, periodic combinations sound nice together? A little bit more than that, and that is that it's possible on a string to get it to vibrate with more than one frequency. So I'll start with that bottom string here. There's its note, but I can get it also to play a note 1 octave higher, or a note 1/12th higher. Can you all hear that? People up the back can't, but I did warn you to come back down. Okay, and 1/4 of the way along. It can actually vibrate in several different ways. Let's look at the pictures of that. So I could say, if I've got a string of this length L from there to there, and I'm going to stop it vibrating from either end, stationary here, stationary there, actually that's what's in physics called first order approximation, or what my mother would have called a lie. I mean, the whole point of having this box on the guitar is that, of course, the bridge has to vibrate. Then that makes the belly vibrate. So this isn't really stationary, but it's almost stationary, approximately stationary. Anyway, if it were stationary, it'd be just an electric guitar. So anyway, here's the length of the string, and here is a wave, and we can see that exactly 1/2 of a complete wave fits onto the string, or the string could vibrate with one complete wave occupying the length of the string if I stopped it in the middle. So there's the whole string, and there is the stopped in the middle, and if I stop it 1/3 of the way along, I could get a wave that's 2/3 the length of the string, like that. And there's a whole series of these. Maybe this is a time where it would be good to have an animation, and I'll ask my physicist mate to have a look at that for us. So let's see, how do I do that on here? Whoa, not interested in that. There we go. So he'll go through all of this for us as well, with the maths for the nerds amongst us, playing all the notes. And yes, here are those.
By suppressing some of the modes.
So notice.
I tune this string to C3, that's the C below middle C. If I touch the string very lightly, halfway along, I suppress the first, the third, and all odd-numbered harmonics.
So it's a little bit more complicated than just saying it's one vibration. You remove a whole family by that touching the note. But it's possible to do that. And I could go through a whole series of notes doing that with simple ratios. So I could go whole, and then half, and then a third, a quarter, a fifth, a sixth, and then the seventh is the first that isn't in our ordinary scale. Can you all hear that up the back? Okay, so let's go again. 1, 2, 3, 4. And then after that I get a little scale. And that scale, incidentally, is also used by buglers and in Bach's time by trumpeters. And you can play bugle calls on those. And so forth. Anyway, so there's that little, the basis of our harmony all there on one string, and just the pure numbers dividing it into 1, 2, 3, 4, 5 parts. Yeah, so there's the whole series there, and if you want, the physicist man will demonstrate them for you. Anyway, he's got such a terrible voice that I don't want to hear any more of him. So there we go. Let's go back to PowerPoint, and there. Okay. So let me show you the way guitarists discover the circle, and then we'll talk about how violinists do it. So if you're a guitarist, your strings are largely tuned a fourth apart. And what you'd say is, well, if that ratio is 3 to 4, then the fourth harmonic on this string should be equal to the third harmonic on that one. So you say, all right, let me take the fourth here, and then I'll make that one equal to the third on that string. And it's a good way of tuning your guitar, well, with some modification. So here, there my guitar is out of tune. And I can just tune it until the beats, more on them later, the beats go away. And then I can do the same for the next string and so forth, and then it gets a bit complicated. Okay, so we all sit there and go, oh, isn't that cute? And then we think, well, what happens if we continue that? And there's the problem. That 4 to 3 ratio that looks like being a basis of harmony is a problem. Oh, and by the way, if you're a violinist, then your strings are tuned in fifths, and so you get a circle of fifths instead. But that stretches the range of an orchestra, so I'm not going to talk about that one. So here's the amazing thing about the circle of fourths. Suppose you did it on a piano, and you went C, D, E, F, F, G, A, B flat, C, D, E flat, and going up and up and up, each time going up a fourth on the keyboard, and then eventually you get to G flat, but on a piano, G flat and F sharp are the same thing. And so when you get to F sharp, you go F sharp, G sharp, A sharp, B, B, C sharp, D sharp, B, and so on. And you keep going And magically, after 12 fourths, you're back to C and you've covered 5 octaves. Wonderful. You've gone through all those terrible keys and you've come back home. Sharps and flats have gone. The sun is shining. We're back in C minor. Good news, yeah? Actually, there's a piece of music that does that starts in A minor and gets back to A minor. And I remember when we first rehearsed that in an orchestra, they'd like to say, oh, we're out of the sharps and heading for home. And there was a sort of sigh from everyone that sort of agreed with me. Anyway, onto that. So wonderful. We close the circle on a piano. The worry comes like this. If I've got 12 fourths, then it's 4 over 3 to the 12th power, and punching that into a calculator, I get 31.6. 2 to the 5 is 32, 4 thirds to the 12th power is 31.6, which are not equal. Not only are they not equal, they're way out. I mean, it's a quarter of a semitone. It's a serious amount. It's called the Pythagorean comma. It's a very old problem, yeah? And how would you resolve it? Well, one way is to say, well, F sharp and G flat are not actually the same. B and C flat are not actually the same. And you just have a spiral. And you just add lots and lots of keys and your keyboard gets deep as well as long. That's been tried, but it isn't the usual answer. One very common modern answer is called equal temperament. But it's worth saying that jumping straight to equal temperament, which I'm going to do, is to leap over a huge amount of work. The number of people who've spent their time, wasted their time, trying to find arithmetic ways of dealing with this problem around the world, Ptolemy, and as I said, a rich Chinese tradition of it as well, and not getting very far, finding compromises of various sorts. It's a huge question. But one way to do it is this. Suppose that you made each of the fourths equal to 2 to the 5/12ths power, that is 1.335. For most of us, that's acceptably close to 4 on 3, which is 1.333. And of course, if you do that, that tunes all of the note names. You can do the rest by octaves. And we could say that the equal tempered semitone has a ratio that is the 12th root of 2, or 5.9% increase. And if I take that R there and I make all of my semitones the same with frequency ratio R, which is almost what we do on a piano, then each pair of adjacent notes on a piano has the ratio 2 to the 12th power, and you multiply 2 to the 1/12th by itself 12 times, and of course you get 2, which is almost the solution to the problem. Only almost a solution because of this. 2 to the 4/12ths should be a major third. 2 to the 4/12ths going up 4 semitones. And the trouble with that is that 2 to the 4/12ths is 1.26, which is not quite the same thing as 5 on 4. So equal tempered fourths are not always a good answer. They're actually a very good answer on a piano, but they're not always a good answer. Okay, so, whoops, what happened there? A problem comes from the thing that we noted when I was tuning, those interference beats. Remember, when I detuned the guitar a bit, and you can hear those. Can you hear the ba 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 between those two? Okay, I could do it here as well. Let me tune that a little bit worse and blow 2 notes there. Can you hear the interference there going loud, soft several times a second? Okay, so that's what we call interference beats. And the interesting thing about those, again, I'll let the Phys Clips man go through the details of that because I want to keep to my musical story. the difference in frequency of the two notes equals the number of beats per second when you put them together. By the way, how many people have heard of interference beats or have used that when tuning an instrument? Yeah? And the rest of you haven't noticed that. Am I making it clear? Can you see how it could be used to tune an instrument? In the green shawl? A bit. Okay, let me do it like this. So, almost the same, but when I blow them together, you can hear that unpleasantness. And if I tune it to get rid of those, now they're in tune, yeah? Just for the moment, take my word that the difference in the two frequencies equals the number of times it's going da-da-da-da-da. And when I'm hearing those da-da-da-da-da, I've got it pretty close. Yeah? That's all we need for now. Is there anyone who's left behind? Anyone bored? Good, good.
Can I ask you a quick question?
Yeah?
Might be a bit off track.
Yep.
Is the reason why you have the dilemma with the mathematics because of 440 tuning or
No, it happens. It happens with whatever you choose as your reference, and yeah, that's an interesting thing. Why you should do that? Yeah, but that would take us a long way. So let's leave it for a moment. Okay, what happens if you take two notes that are further apart, a long way apart? Can you hear that difference? So what I'm going to do is, because I'm using those little recorders, I'm going to hold one note constant on a high G, and the other one I'm going to play a note close to B, C, D, C, B, going backwards and forwards. And if I play those with the nice Pythagorean ratios, the ratios would be for a major third, 5/4, for a fourth, 4/3, and for the fifth, there's G, A, B, C, D. The fifth, that would be 1200/800 hertz. Can you see where I got my numbers from? Anyone not? Okay, so here are my neat Pythagorean ratios, and those are roughly the frequencies of the notes that I'm going to play. And just suppose I could hear the interference between those two. That would be 200, 267, 400 vibrations a second, and then coming back down. Yeah? If I could hear those, they would be ghostly notes, which is why I put them in grey. Ghostly grey notes way down lower. And I think most musicians, when they first hear these, think, that is amazing. I still remember one summer afternoon playing chamber music with some young friends and hearing these ghostly notes and thinking, wow, that is seriously weird. So what I'm going to do is play... What I'm asking you to listen for is some notes close to la, 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 la. Okay, high my voice, but obviously well below the range of these high-pitched instruments. Now, this is one of the reasons why I wanted people to sit close to the front, because you hear these best when they're loud, so I'm going to come close to everyone and hear them, and I'm hoping that a good majority of you will hear them. But let's find out. Can you hear the beating there? Yeah. I did warn people at the back that they'd miss out on demonstrations, but yeah. Particularly if you get really close. How many people are sitting there saying, I can't hear anything, he's off his head? How many people have heard those strange ghostly tones out the bottom? Okay, but the people who have, those who haven't, next time sit close to the front of the lecture theatre, but you can go to the physicist site and hear them as loud as you like in the privacy of your own headphones, and we can You can then decide whether they're there or not. But it's an interesting thing. And the problem here is this. Supposing that instead of doing it with this tuning, the tuning that preserves these neat ratios, here are the intervals you would get if you did this on a modern piano or a modern keyboard. These are the 2 to the 1/12th semitone numbers, and they're quite different. Look what it does to the third. If I used not 1,000 hertz but 1,008 hertz for the equal tempered interval, my difference frequency is a long way different. Now you might think, well, it's not a problem, you just get the different weird note. The problem arises in a musical context because this, supposing that the flute is playing the high B, the oboe is playing the G, and sitting behind them are the clarinet and the bassoon trying to play a bass note. And if they're playing this 200 hertz, that's exactly 2 octaves below the oboe's G, they're just not going to be able to do it. It is just too uncomfortable. And so in a sustained woodwind chord with no vibrato, you just have to do something about it. And the thing that musicians do is they just tune to the simple ratios. And you often get music, you know, when an orchestra gets their music from the higher company or the ABC library, it's often got little arrows written over the notes to tell you what to do. So just briefly, equal tempered thirds are not good enough. You can't fix everything, but you can compromise, and there are any number of solutions to that. We have actually an expert in harpsichord playing and therefore in temperament sitting here, Wait Song. Okay. About how many temperaments would you say are in common use in harpsichord players?
Maybe 4 or 5.
Maybe 4 or 5? Werkmeister and Velotti and Young and some of the world temperaments, yeah? And Bach, of course, wrote in one of the world temperaments before, you know, people were taking equal temperament very seriously. Anyway, you can do various things. There are various of these arithmetic compromises, which I'm calling the arithmetic resolutions to the circle. But I promised I'd tell you about another resolution to the circle, a musical one. Now, from here on, it's self-indulgent because I'm going to talk about one of my own pieces. But when I first decided I'd talk about this to a physics audience, I ran it past a couple of colleagues to try, and they said, Joe, you should shorten the first bit and expand the second. It was much more interesting. So I did, and for you, that's why I'm going to do it as well. I'm going to talk about the why and the how of writing for, you know, a bunch of 60 or 70 musicians, and also the question of why I think it's interesting to examine that process. I'm not a musicologist, but here's the thing that interested me. A note processor is the musician's equivalent of a word processor. And in the 1980s, they first sort of became available just like word processors. And so that was the first time I started writing music with a note processor. And in those days, before Microsoft appeared, the size of the file was related to how much work you'd done. You know, you write a letter to somebody and it says, oh, 3K of memory required. You know, now you open Microsoft Words and it's 5 megs gone already. Anyway, so I used to write music and look, how much work have I done today? How big has the file got? And then the weird thing was it wasn't very satisfying. And the first time I noticed this, I was writing a 20-something minute piece for full symphonic orchestra. And the file sizes were small. And I realized, actually, yes, they are small because music is redundant. It has pattern in it. And any sort of pattern reduces the total amount of information. So I studied this. I started looking and calculating, you know, how much information is there in simple musical motif, and then when you convert this to short score or to long score, how much extra information do you put in? And that's the information that goes to the conductor or the player. And then this huge analog signal, huge bit stream comes out of the instrument and goes into your ear. And into your ear, there's a little bit of mechanical analysis that happens in the inner ear, and then you get a semi-digital, combination digital analog signal going to the brain, and then some information analysis of that, and maybe the person who walks out of the concert hall has regained the very original motif that went into this. And I had huge fun talking about this in terms of quantity of information and a little bit of information theory. And for a while, at the end of last century, that was a party piece of mine. I went around the country lecturing about this, and people said, oh, that was a fun talk, and someone would invite me somewhere else. And eventually, at the end of one of these talks, a couple of industry executives came up and said, you're the man for us. We have an industrial problem for you to work on. And that's how we started the UNSW Acoustics Lab. It started on that industrial collaboration. Anyway, it's quite a lovely story, so if you're interested, I'll talk about it afterwards, but I don't want to get off the talk too much to say, but if anyone wants to look at the publication on our lab website, there's the paper about it. Okay, the Circle of Force, the overture, it was commissioned for University of New South Wales Orchestra's 100th concert. And as you'd expect from a technical scientific university like this, the orchestra has a certain number of music students, but has a much larger number of science, engineering, medicine and other students in it. And we'd been talking about this circle and the problem of temperament. And so that was the idea when they asked me to write a celebratory overture for the 100th concert. Joe, why don't you put the Circle of Force in? You know, build it in. I said, you mean as the chords? Yeah, how about a chord? What do you do? So that was the dare was on. Does everyone understand where I'm coming from now? Because we're now in a music store. And then, so that was the first thing that went in. And then there are a few other constraints. And so here are by the way, this is the University of New South Wales Orchestra there. And you'll notice that there are a few elderly people, an elderly very elderly bassoonist there. But so there's staff in there as well as students is my story. Okay, so here are the constraints. 5 or 6 minutes for an overture for full symphony. Full symphony, you want to give everyone something to do. Using the circle of fourths. There's good reasons for not using the circle of fifths. 100th concert must feature the number 100 prominently. And not in an arbitrary way, like 100 bars, no one would notice because barring's a bit arbitrary where you put the bar lines and no one counts anyway. Even the people resting at the moment count. They rely on the conductor to wake them up. Anyway, because on your 100th concert you do an interesting program, there was lots to rehearse. So this had to be fairly simple, easy to play, probably tonal. Anyway, there are a few other constraints. I also wanted to put my little signature. 985 is something that I often write into music. There's a sort of, graffiti in the corner. And you might look at this and say, gee, Joe, why are you giving yourself all those constraints? Constraints are good. I think it's true of any artistic endeavour that being constrained actually makes it easier. Like if you're a poet and you're going to write blank verse, then you start off looking at a blank page. The blank page. But if you're a poet and you're going to write a sonnet, then you've only got 14 blank lines or 70 blank feet, which is much less intimidating. I mean, you do have the heritage of Shakespeare to deal with, but in a sense, constraints are good because they limit the possibilities. The second thing is, as I've said before, you can start with a motif. You don't actually need much material if you have enough constraints and enough algorithms. So, here's the lesson. How to compose. Write down the notes one after another until you get to the end. Yeah, so first of all, you need something to generate the nucleus of a tune. And there are various different things that you could use. So Mozart's alleged to have pinched tunes from his canary. Canary's agent wasn't sufficiently active. It might be, if you're Beethoven, Fate knocking on the door. Or if you're Bach, it could be B-A-C-H. If you're Martin Wesley Smith used to teach composition at UCID for a long time, and he had a range of these that he would use, I think partly as a joke for him and his students. One famous one called White Knight and Beaver, he just found the DNA code for some E. coli, the little bacterium that everyone was studying at the time, and he just pinched all those notes, made a one-to-one transcription to pitch the numbers, their base shorthands, and transcribe that. And then, once you've got a nucleus, a few notes to get started with, then you need some way of extending it to make a tune. But the one thing you do find if you look up a book on composition, which I have from time to time, is that there are algorithms for doing this, like repeat it, move it up and down, turn it upside down, turn it back to the front. There's all sorts of ways of making it longer. And then the most important one in composition is once you've generated some ideas and extended them, you have to decide which ones to keep. And obviously that's the important one because you want to choose the good ones. Now, what's a good one? Well, that's a completely different question. A question about taste, what's good, what's bad. We've already had a little dispute about that in this lecture so far. I mean, there's no way, certainly no way a physicist wants to talk about that. But at least I can say this. At least I can say that the most important part in composition is the one bit that everybody knows. You're all capable of making a decision. I like this, I don't like that. This is good, this is bad, for me anyway, yeah? So the thing that is the most important step for a composer is the step that's also the one that everyone knows how to do, which is kind of useful. So though it may be a difficult psychological question, it's easy for us all to empathise with it. And then there's orchestration, which can be complicated if you want to do it well, but there are some good paths to follow there, and again, some algorithms there. Incidentally, I've put asterisks there because for me, all of these seem to be much easier when I walk along the cliffs at Coogee. So my way of writing music is to have a little piece of score paper, almost blank at the moment, in the pocket and go for a walk and, idea, write it down. And I have a number of little algorithms that I process in that way. So if you have an algorithm for generating sources of some sort, look at the numbers on car number plates, listen to canaries. Seagulls aren't very good. But anyway, if you've got something that will generate a few notes, some way of extending, and most importantly, are capable of deciding which ones you like and which ones you don't, you're on the path to making up a tune. So, what did I do in this specific instance to illustrate that? Oh no, sorry, before that, here's a famous one. Here's this fate knocking on the door business. Repeated quavers, incidentally starts with the most famous rest in musical history. 3 repeated quavers, then go down 3 notes. Oh, and then what do I do after that? 3 repeated quavers, and go down 2 notes again. 3 repeated quavers, go down 2 notes. I'm going down only 1 note. 3 repeated quavers and go down. So you can make quite a meal out of not very much food if you're Ludwig van. Let's just hear that as we go. Yeah, that's as loud as it goes. And so forth. Anyway, he runs that tune by you for almost the whole of the first movement, so much with so few little variations that by the time you get to the horn entries, the horn comes in and they go down 4 notes. Ya-ta-ta-ta-ta-ta, it sounds completely new. But yeah, obviously you're being sold a pup here. It's the very simple change in the whole. Anyway, so you can do a lot with not much material. And so I decided I would do that as well. And then here's the constraints and what I'm going to do. Well, for the 100, I thought, what about the old 100th? The old 100th is the name of what used to be number 100 in the hymn book or the chorale book. Any religious people here? Does anyone know the... All people that on earth do... I should have got you to sing before. Yeah? Anyway, so it's called the old 100th. And I thought, I'm going to pinch that as my nucleus. Yeah? Now, on the one hand, you want to be recognised pinching it because I had to satisfy my 100. But you don't want to pinch it straight away. So what I did... that theme is just 8, 8, 7, 6, 5, 8, 9, 10. So I decided I'd do that. Repeat a note, then step down, then step down, then step down again. But I changed it. Instead of going 8, 8, 7, 6, 5, I moved it up a note, put it in a minor key and went 9, 9, 8, 7, 6. Changed the rhythm a bit as well. I think if I hadn't told people this, they might not have even known where I got my idea from. But here is that little 9, 9, 8, 7, 6, used in a different key. Let's run that little bit there. Whoa, go back. So you can take a few notes like that and develop it into an extended tune. Let's see, have I got this as loud as it will go? We need some volume up there. Yeah, we could go up a bit louder. Okay, so just a bit louder. So just moving things up and down and repeating, and it makes it, you may not like the tune, but you can certainly call it a tune and get something out of that. And then, well, one tune's not enough to make 6 minutes worth of orchestral music. And I think I told you that 985 was a little graffiti signature, a tag that I often put in music. And so I thought, let me do the same thing. Instead of going 9987, I'd go 9985. So I got my little tag in there, and then jump up an octave. 9, 9, 8, 5, 12. And so here's that little tune. Or it's obviously a variation of the first tune, and so you can get away with that. It sounds like development, and people think that you're a well-trained composer instead of a self-taught brat from the working class. And then the next step was to get something completely different. How about precede the repeated note stepping down with a couple of fourths? After all, I'm going to put in the circle of fourths chord. So 5, 8, 11, 10, 10, 9. So here are 2 fourths followed by my little old hundreds story. And let's see how that works as a tune. Okay, so another variation that we can use for contrast and put the whole story together. So then, back to that question. Remember that tough guy walked into the room chord? How am I going to get from that really strange sound back to the sort of tonality that I've sketched in the rest of this story? Well, there are 2 obvious things that you can do, and in the bit of music I'm going to play you later on, they're here. You could start with that chord and very gradually, in steps, end up with something satisfying to end. You could say chord, 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 sort of the way you do it in standard music. And so I used that twice in 2 variants towards the end of the piece. And early on in the piece, I had another idea. Why don't I leave half the orchestra playing that weird chord and take the others and either gradually and quasi-continuously converge on a chord, or else do it, more discreetly and synchronously. So I'm going to play the piece and I'll indicate where that, oh no, I don't need to. You'll hear that chord when it comes, and you'll see and hear the solutions that I've tried to put in. So just to remind you that funny chord. It's kind of funny, when we first rehearsed that with UNSW, the conductor said, is anyone playing C in this chord? Yeah. Anyone playing C sharp? Yeah. Anyone playing D? And he went around and said, oh, this is going to be an interesting chord. Anyway, so that's the strange chord. Let me now escape out of that. And what I'm going to try to do is play this and walk through the score with you. Anyone experienced at reading an orchestral score? Okay, in that case, the man in the green shirt is going to read this and turn the pages, and a conductor, if you'd like to... Yeah, but I mean, you can follow the first fiddle part, and if you'd like to watch it in hard copy and see just how fast the conductor has to turn pages. So everybody's part is written down for the conductor, so if you'd like to watch that on hard copy, he'll have it. If you want to do it on soft copy, you'll depend on my clumsy mouse control, which is a bit, it doesn't work all that well, but let's see how we go. So we've got to have, there's the recording, and where's the score? There's the score. Does it fit on? Yeah, almost. So we go right back to the beginning. Whoa. Okay, so get that ready to go, and here we go with recording. There are my fourths. So that's my ending. You could have stopped at 4 bars from the end, but it's just a matter of taste.